You're sitting in the dark, listening to the wind howl. On your phone, you see the utility company's alert. Grid instability, rotating outages in effect. And you think to yourself, this is the 21st century. We have smartphones that talk to us and cars that drive themselves. So why does the entire system that powers our civilization still buckle under a storm? It feels medieval. But here's the contradiction that should keep you up at night. Our electrical grid isn't failing because it's old. It's failing precisely because it's modern. This is the energy historian, uncovering the hidden systems that power civilization. Think of the grid not as a single machine, but as the world's largest, most complex, and most delicate balancing act. It must perform a real-time magic trick, 24 hours a day, generate exactly as much electricity as is being consumed, at the very instant it's consumed. There is no giant battery in the sky. If demand spikes upward faster than supply can respond, the frequency of the alternating current drops. If it drops too far, protective relays begin automatically disconnecting power plants to save them from catastrophic damage. That's a blackout. The entire system is held together by a gossamer thread of perfect equilibrium, and we've spent the last century making that equilibrium harder and harder to maintain. We built the first grids for a different world. They were regional, powered by a few massive predictable generators called plants, hydroelectric dams. They were dumb but robust. The operator's job was simple: forecast demand, spin up the big machines to meet it. The system was overbuilt, with plenty of slack. Then came the modern era. We connected everything into three giant synchronized networks: the Eastern Interconnection, the Western, and Texas. We added nuclear plants that can't ramp up and down quickly. We introduced market mechanisms that prioritize the cheapest kilowatt hour this second, often from thousands of miles away. We replaced that overbuilt slack with ruthless efficiency. We turned a robust, muscular system into a hyper-efficient, just-in-time network. And in doing so, we eliminated its immune system. Now, layer on the first modern complication: the weather itself. We didn't just make the grid more efficient, we made it more exposed. To chase cheap land and avoid local opposition, we built sprawling wind farms on the Great Plains and massive solar arrays in the desert southwest. This is clean power. It's also intermittent power, located far from the cities that need it. So we built long-distance, high-voltage transmission lines to bring that power home. You've created a continental-scale energy supply chain. And what is a chain? It's only as strong as its weakest link. A blizzard in Nebraska can now cause price spikes in California. A heat dome over Portland can threaten rolling blackouts in Arizona. The grid is no longer a local balancing act. It's a national tightrope walk, and the weather holds the pole. But here's where the real tension enters. We added all this weather-dependent complexity, while simultaneously neglecting the physical backbone. The average age of a high-voltage power transformer in the United States is over 40 years. Much of the transmission infrastructure is from the 1960s and 70s, designed for a cooler climate with less extreme weather. The system is trying to perform a digital age, real-time balancing act on analog-era hardware. It's like asking a Formula One car to run on a dirt road from the 1950s. The software is cutting edge. The physical platform is crumbling. Let's make this concrete. February 2021, Texas. The temperature plunges. Demand for heating skyrockets. But the supply side collapses. Natural gas wells froze. Wind turbines iced over. Nuclear and coal plants tripped offline because their intake water pipes froze. The market signal screamed for more power, but there was no more power to give. The system frequency began to drop. To prevent a complete, months-long blackout of the entire Texas grid, the operators had to manually cut power to millions of homes. Over 200 people died. The financial cost topped $130 billion. This wasn't an old grid failing. This was a modern, market-optimized, lean grid failing because it had no buffer, no redundancy, and no plan for a correlated shock where the demand spike and the supply collapse were caused by the same event. Cold? The Texas freeze is the purest example, but the pattern is everywhere. California's rolling blackouts during heat waves aren't about a lack of sun. They're about the sun setting just as everyone turns on their air conditioners, while the imported power from other states is also stretched thin. The Northeast's vulnerability isn't just to snow, it's to trees. We built a grid that depends on long, delicate transmission corridors through forests. A major storm doesn't have to hit a power plant. It just has to knock one key tree onto one key power line, and the cascade begins. The modern grid is a system of immense leverage, where a single point of failure can ripple outward at the speed of light. So we face a paradox. To decarbonize, we need more weather-dependent renewables. To make those renewables work, we need more long-distance transmission to smooth out local weather. But more transmission creates more points of failure and makes the grid more complex to balance. It's a trilemma: clean, reliable, cheap. Pick two. For decades, under deregulated markets focused on cost, we picked cheap and eventually clean. Reliable, in the face of worsening weather, was the assumption we stopped actively engineering for. We traded the robustness of the old dumb grid for the efficiency of the new, smart one. And now, the weather is presenting the bill. What's the way out? There isn't a simple one. It's a structural recalibration. It means building a grid that is both more decentralized and more interconnected. Microgrids with local solar and batteries can island themselves during a wider outage, creating pockets of resilience. But we also need stronger, more hardened transmission superhighways to move power across continents when regions are in trouble. It means building redundancy back into the system, keeping old, inefficient power plants on cold standby for emergencies. It means burying power lines in critical corridors at colossal expense. Ultimately, it means redefining modern. A modern grid isn't just the most efficient one. It's the one that can withstand the storm we know is coming, and the one we don't. The next time the lights flicker, remember what you're seeing. It's not a failure of technology. It's a failure of design philosophy. We built the perfect system for the 20th century, and then we changed the century and changed the climate, but left the architecture on autopilot. The grid isn't failing because it's old. It's failing because its modernity is incomplete. A brilliant digital brain bolted onto an aging body, trying to navigate a world that is becoming physically wilder by the year. The question isn't how we patch it. The question is whether we have the will to rebuild the underlying logic. If this gave you a new perspective on the lights above you, hit subscribe. Let me know in the comments, is the trade-off for cleaner power a less reliable one, and are we willing to pay the true price to have both?